All right, so what we're going to do today, we'll just do some examples using impulse momentum theorem or just momentum conservation. So here's the first one. A 10-gram bullet is fired into a 1-kilogram wood block where it lodges. Subsequently, the block slides 4 meters across a wood floor. What was the bullet's initial speed? Okay, so I think it's a good idea to draw a picture. Anything else want to go wrong? So we'll draw a picture. Okay, so here we have this block, and we have a little bullet, whatever. And what we want to know is the velocity of the bullet initial. Okay, so that's what we want to know, velocity bullet initial. Okay, so the bullet, is moving towards the block. Let me do that nicer. Okay. So that's before, and then this is after. So afterwards, so we have the bullet in the block of wood. All right, that's the bullet in the block of wood. And then the block of wood is going to move 4 meters. Okay. So I'm going to call this x wood 0 and velocity wood 0 and x wood 1 velocity wood 1. Okay. All right, here you go. All right, so that's what's kind of going on. All right, so there's a collision. So we got to deal with the collision first. And, you have this 10-gram bullet fired into a block. Now, just for the collision itself, we can ignore friction. We certainly can't ignore friction here, when the block slides to 4 meters. But just for that super fast collision, we can ignore friction. Okay, so if we ignore friction during the collision, what's conserved? Well, there are no horizontal forces then, right? External horizontal forces. And so momentum is conserved. So let's do it. Okay, so this is just for the collision. All right, so mass, bullet, velocity, bullet, initial, plus mass, wood, velocity, wood, initial, which is 0, right? Equals, okay, all right, equals mass, bullet, plus mass, wood, velocity, wood, initial. Okay? All right, so before the bullet's moving, this is stationary, so this is 0. Afterwards, we have the mass of the bullet and the mass of the wood, right? And we have the velocity. I'm just going to say velocity wood initial. It's really velocity wood plus bullet initial, but that's too much to write. Okay? So that's just momentum conservation. All right? Now, what we want is this, so we just solve for it. All right? So this is 0. So just divide by the mass bullet. Mass bullet. And there we go. Now we have velocity bullet initial equals this thing. Let me write it nicer. Velocity bullet initial equals that. All right, awesome. So we're done, right? Wrong. All right, so we're not done. Why aren't we done? Because, okay, we know the masses and everything, but we don't know what the velocity of the wood initial is. Ah, rot. Okay, So we don't know that. All right, but hold it. This is just kinematics, right? I mean, you know, this stops here. You know, we know, look at, we know velocity, we know the velocity, we know the distance. So kinematics. So what kinematic equation will help us? All right, so after collision, so we have, so V final squared, which is V wood 1 squared, V wood 1 squared equals V initial squared, V W0 squared. Okay, so V final squared equals V initial squared plus 2A delta X. Well, that's cool, right? Now, this is 0, correct? Because the wood stops. So this is 0. Okay, so we wanted VW0. There it is, right? So VW0 squared equals minus 2A delta X. So the square root is this. Now what's the problem now? We don't know what A is. So what's A? This is kind of how these problems work, right? You're trying to get something and you realize you need something else. Then you get that and you realize you need something else. Then it just keeps going, for a while. All right, so now we need to know A. Well, how do you get A? How do we always get A? Force diagram. So let's get a force diagram, but I need some space. Hope I didn't erase anything important. So force diagram. All right. So let's do it. So remember, this is after the collision, right? After the collision. So what are the forces? I shouldn't have removed my picture. Oh, well. All right. Well, what are the forces acting on the wood with the bullet in it? Well, there's kinetic friction this way. There's a normal force that way. And there's gravity down. And the gravity down is the m wood plus the m bullet times g. Okay, we can do it, right? We can do it. Now, what do we want? We want A. Well, let's go. Well, okay, so let's skip a couple of steps here. It's not accelerating in the y direction, so therefore we know that the normal force is m wood plus m bullet times g, right? That's just the sum of the y's. Okay, now we want to get A, right? So we can do the x. So sum of the x forces. Sum of the x forces. Well, there's only minus k, and that's equal to minus mu kn, which is minus mu k, that thing, minus mu kg, m wood plus m bullet. And of course, what does that equal? ma. But what's m? Mass wood plus mass bullet. So mass wood plus mass bullet times A. All right, so sum of the force equals ma. No kidding. So therefore, remember, we're trying to get A. Let's just look here. Okay, so divide by mass wood plus mass bullet, and it gives us A equals minus mu kg. Now, notice it's negative. Well, no kidding. I mean, when the block is sliding to the right, it's slowing down. So the acceleration has to be negative. So that's good. All right, so we figure this out. So minus 0.2 times 9.8. Okay, so that comes out to be minus 1.96 meters per second squared. Awesome. Okay, so now we can figure out this. So minus 2, you might have been worried about a minus here, but since that's negative, it's going to be fine. Delta x is 4 meters. And that comes out to be 3.96 meters per second. So that's this. All right, now where do we want that? Right here. All right, now we can do it. So this equals mass block plus mass bullet. So that's 0.01 kilograms. That's a gram. That's mass of the bullet plus mass of the wood is 1 kilogram divided by the mass of the bullet times velocity wood 0, which is what we just calculated. And you get 400 meters per second. Wow, that was a lot of work. All right, so 400 meters per second. Does that sound reasonable for a bullet? Yeah, it sure does. Okay, so look at that. Right? Now, why did we ignore friction during the collision? Well, it's just that, you know, the force from the bullet hitting the wood was so much greater than the force of friction. We can just ignore the force of friction, okay? So that's why. But you know, we had to ignore friction during the collision, because if we wouldn't have ignored friction during the collision, we wouldn't have had momentum conservation. And then what do you do then? You don't do anything. You're stuck, all right? So, all right. So why did we use momentum conservation? Well, because, like, you know, there's a before and an after, right? I mean, generally speaking, when there's a collision, you know, there's a before and an after. So if it's an isolated system, you can use momentum conservation. So there you go. That's a pretty challenging problem. So make sure you understand it. It's just one of these problems where you just have to keep plugging away, keep plugging away. You know, don't get discouraged, because you just have to keep, you know, do the next step, do the next step, do the next step. But we didn't do anything difficult. We just had to do a lot of things. So good problem. Okay, so that's that. So that was nice because, I mean, yeah, I say good final exam question. Why do I say that? Well, we had a collision, so we used momentum conservation. Then we had kinematics, but we had to find acceleration, so we used force diagram. I mean, you know, that's a good final exam question, right, with all those different concepts. So study that one. That's a good one. Okay, so read that while I erase. So this is momentum conservation, which I guarantee you will have a momentum conservation problem on your exam as well as the final. Okay, the radioactive carbon isotope carbon-14 is used for carbon dating of archaeological artifacts. Carbon-14 decays by the process known as beta decay, in which the carbon-14 nucleus emits an electron, which is called a beta particle, and the antineutrino. All right, so you have the carbon-14, it spits out an electron and an antineutrino, and what's left is the nitrogen-14. Okay, in one carbon-14 decay, the electron and the antineutrino are emitted at right angles. Okay. Or who knows what, right? I mean, it could be like, I mean, I don't know. They're just right angles. We don't know where, but just right angles. The electron has a speed of whatever. The antineutrino has a momentum of whatever. What is the recoil speed of the nitrogen-14? Whoa. Now, so we have a before and an after, right? I mean, we start off with this carbon-14, and then all this stuff is created. So how do you approach it? Well, usually when there's a before and an after, something is conserved. You know, so you have your choice. Is it an energy problem or a momentum problem? Well, notice they have momentum, mass, speed, right? Momentum is mass times velocity. So this is probably going to be a momentum problem. Okay, now we've got to make some assumption. So what do they tell us about the carbon-14? Nothing. So what are you going to assume? I mean, they don't tell us it's moving, so what's the only thing, what's left? What do we have to assume? We're going to assume it's at rest. Well, I mean, what else can you do, all right? Okay, so that's a big deal. So if the carbon-14 is initially at rest, then what's its momentum? 0. Okay, are there any external forces here? No. I mean, You know, there's no external forces, right? And so we're going to say that, so we're assuming that the decay is along the horizontal plane, let's say, or some plane. And so we're going to ignore gravity. That's okay, believe it or not, because the masses of these things are incredibly, I mean, look, you know. So we're going to just assume we can ignore all the forces. And so it's an isolated system, so momentum is conserved, okay? That's kind of a lot of assumptions, but it works, okay? It really does work. Okay, so we're going to say, so P initial equals P final, which is our favorite number, 0. But you know, you have to go through all that thought process before you can even start it. Okay, it's probably nice to draw the thing, so let's draw it. Okay, now all we know is that the electron is perpendicular to the neutrino. So, I don't know, just pick something. Doesn't matter, as long as they're, you know, at right angles. Okay, so let's pick that, okay? Why not? Now remember, we started off with the carbon-14 at rest. And then, you know, it spits out the electron and the antineutrino and a nitrogen. Okay, so we want the final momentum to be 0. So therefore, what has to be the direction of the nitrogen 14? If we want the momentum of this to be 0, well, it has to be down here somewhere, right? Okay, so there's the nitrogen. All right? So you can imagine that that plus that plus that equals 0. Okay? It's like that lab, hopefully you did already, when you had the, what is that called? You had a circular disk, and you hung masses from it, and you balanced the forces. The force table, yeah. So it's kind of like a force table, right? You have to balance this and this and this, so the momentum is 0. All right, woo, here we go. Okay, so momentum. So you know, we have an x direction, we have a y direction. So let's just be boring and call that x and that y. All right, okay, let's do the x. So this is the px. All right. So we have the momentum of the electron. So mass, electron, velocity, electron in the x direction, plus mass, nitrogen, velocity, nitrogen in the x direction. That has to equal 0, right? It has to equal 0. Okay? Because of that. So therefore, the velocity of the nitrogen in the x direction equals negative mass, electron, velocity, electron, x over mass, nitrogen. Well, we can do that, right? So we know the mass of the electron, so minus, where'd it go? 9.11 times 10 negative 31 kilograms. Velocity of the electron in the x direction is what? 5 times 10 to the 7th. 5 times 10 to the 7th meters per second. It's all in the x direction, right? Mass of the nitrogen is 2.34 times 10 minus 26 kilograms. So you do that, and you get minus 1946 meters per second. Okay, so that's the velocity of the nitrogen in the x direction. And notice it has a minus sign, which it better have because it's going down, right? So it's going to have a minus x component and a minus y component. Okay, let's do the y. Yeah, much better. All right, let's do the y. So the mass of the neutrino times velocity. Oh boy. Okay, so the neutrino kind of goes like that. So the mass of the neutrino, velocity of the neutrino in the y direction, plus the mass of the nitrogen, velocity nitrogen in the y direction has to equal 0. No kidding. So therefore, the velocity of the nitrogen in the y direction is equal to negative mass neutrino, velocity neutrino in the y direction all over the mass of the nitrogen. And we can do that. Now this is the mass of the neutrino times velocity neutrino. That's just the momentum, right? That's just minus momentum neutrino in the y direction over the mass of the nitrogen. And they give it to us. Isn't that nice? We don't have to multiply. So the momentum of the antineutrino in the y direction, I mean it's in the y direction, 8 times 10 to the minus 24. Minus 8 times 10 to the minus 24 kilograms times meters per second. And nitrogen has a mass of this, 2.34 times 10 minus 26 kilograms. And I promise you, you do that, and you get minus 341, minus 341.9 meters per second. All right, so now we have the x component of the velocity and the y component of velocity. So, and they want to know the speed, which is just Pythagorean theorem, right? So the velocity, the speed of the nitrogen, which is this, if you want to be picky, right? It's just the V nitrogen x squared plus V nitrogen y squared square root of. So it's that thing, 1946.6 meters per second squared plus that, 341.9 meters per second squared square root of. You do that, you get 1976. Fine. 1976.4 meters per second. There you go. Right? All right. So just momentum conservation in 2 dimensions, the x and the y. That's all it is. But I mean, the important thing is, though, you had to set up the problem correctly. I mean, if you know that these two are at right angles, you realize this has to be in that direction. All right, make sure you can do that. It's a good problem. Good problem. Okay, let's see. All right, this is a short one. Let's do a short one. Okay, this is kind of like a total math problem, right? So you have some force, 10 newtons times the sine of 2 pi t over 4. So, all right, so you have a varying force, right? So you know you can't use kinematics. You got to use impulse momentum. Okay, it's exerted on a 250-gram particle during an interval 0 to 2 seconds. If the particle starts from rest, what is its speed at 2 seconds? So think about it. You got this wacky force, right? You have a force that varies with time. No kinematics. The only thing that we know is impulse momentum. Okay, so impulse is the integral of force times time. So you have a force, you have a time, so you can get the impulse. It starts at rest, so you know the initial velocity. We want to find the final velocity. That's impulse momentum theorem. But you have to be able to figure that out. I mean, you have to be able to say, okay, that's impulse momentum, you know. Okay, so let's do it. Okay, so let's just write down impulse momentum theorem. So J, the impulse, equals F dt, which is equal to delta P, which is equal to mv final minus mv initial. Okay, Or, you know, okay. So there, but what's, okay, but what is, what's initial? It's 0. So goodbye. All right. So therefore, V final is just the impulse divided by the mass, which is just the integral f dt divided by the mass. So it's a calculus problem, right? I mean, let's be honest, you know. Okay, so let's do it. What do you say? All right, so therefore, V final, okay, the mass, where's the mass? 250 grams, so 0.25 kilograms. 1 over 0.25 kilograms. And then it's the integral. The time goes from 0 to 2. The force is 10 newtons. We'll put that outside, might as well. And then it's sine 2 pi t over 4 dt. Awesome. Okay, so first of all, it doesn't matter, but what's 100 divided by a fourth? 40. Okay, so we have 40. And, okay, so we have 40. And then what is the integral of sine? You got to know that, right? What's the integral of sine? It's minus cosine. So we have minus 40 integral, oh, sorry, what am I saying? Okay, so integral of sine is minus cosine, but then you got to chain rule it, right? So you're going to flip that thing. So we have the minus 40, and then we have 4 over 2 pi. Then we have cosine of that thing, 2 pi t over 4. And then it goes from 0 to 2. And I get my minus sign. Okay, so let's see. So 4 over 2 is 2. So 2 times 40 is 80. Then this 80 over pi. So we have minus 80 over pi. Okay, so minus 80 over pi. Okay, so put in 2. So we'll have 2 times pi. 4 pi divided by 4 is just pi. So we have cosine of pi minus, and you put 0, you have cosine of 0. Okay. So what is the, okay, what's cosine of pi? Negative 1. So this is negative 1. What's cosine of 0? 1. So negative 1 minus 1 is minus 2, right? So you have 160 over pi, right? Which is about 51 meters per second. There you go. So that's just a math problem. Make sure you know how to do it, though. Okay. One last problem. Oh, yeah. Another kinematics, impulse, momentum, the whole thing. All right, a 200-gram ball is dropped from a height of 2 meters, bounces on a hard floor, rebounds to 1.5 meters. Figure below shows impulse received from the floor. The average force the floor exerts on the ball equals 1/2 the maximum force the floor exerts on the ball. What is the maximum force? Oh, man, make it difficult, why don't you? Okay, so here you go, right? So, okay. So this is kind of similar to the one that we did a while ago. So all right, so let's do it. Okay, let's do it. Pictorial representation. How many points do we need? Just like the last time, 4, right? Up here when it's dropped, before it hits the right before it hits the floor, right after it hits the floor, and then when it bounces back. So, and okay, so here we go. So y0, v0, y1, v1, y2, v2, y3, v3, which is 0, right? And this is 0 too, right? Okay. So I'm being a little lazy. Okay. All right. Okay. So let's see. What do we know? All right. So let's put the origin here. well, in other words, y equals 0 is going to be the floor. Kind of makes sense, right? So y0 is 2 meters. I already said v0 is 0. Y1 equals 0. I don't want to do that. So y1 is 0. v1 we don't know. Let's see. y2 equals 0. v2 we don't know. y3 equals 1.5. And v3 equals 0. Oh, that's great. But what do we want to know? The maximum force? Oh, that's weird, right? That's what we want to know. So this is weird. But that's OK. We'll get it. But wait a second. How in the world are we going to get maximum force? Well, remember impulse momentum. J equals integral f dt equals delta p equals mv final minus mv initial. Save the best for last. Equals f average delta t, right? OK, so we're going to figure out the impulse. And then we're going to say that's equal to f average delta t, right? And then it says that the average equals 1/2 the max. So if we get f average, you know, so the max is 2 f average. So that's how we're going to do it, all right? And so you've got to be able to recognize that. But seriously, as soon as you see this weird force that varies with time, you know impulse momentum. What else is there, you know? OK, so in order to do this, we've got to know these two velocities. Well, how do we get v1 and v2? Our good old friend, kinematics. OK, so I'll probably have to write that again later, but that's all right. So let's get v1 first. So v1, good old kinematics, right? So v1 squared equals v0 squared minus 2g. I was going to say delta y, but let's be good. Y1 minus y0. OK, so therefore, OK, v0 is 0, so that's awesome. So goodbye. So what else is 0? Y1 is 0. OK, so that's 0. And so I just have v1 squared equals 2gy0. Awesome. So v1 is just the square root of that. So square root 2, 9.8 meters per second squared. Okay, y0 is 2 meters. So that's nice. But wait a second. I took the square root. What's the sign? It's minus, right? Don't forget that, right? I know v1 is negative, right? So when I take the square root, I choose the negative. So it's minus 6.26 meters per second. OK, so v1 minus 6.26 meters per second. That wasn't bad. It's good old kinematics. Can do that. OK, now let's get v2. All right, let's get v2, because we don't know what it is, right? So let's get v2. Just use that same old equation, right? So v final squared equals v initial squared minus 2g delta y, right? Delta y is y3 minus y2. OK, well, what is y2? It's 0. So let's get rid of that. So let's just write like that. y3, OK? Now, what's v3? It's 0. Get rid of that, all right? So we have v2 equals v2 squared equals 2g y3. Then take the square root. Again, we know. So what's the sign, though? What's the sign of v2 after the collision? It's up. So this is perfect. Plus sign. So 9.8 meters per second squared. y3, where'd it go? 1.5. So that comes out to be 5.42 meters per second. Again, just our good old kinematics. So v2 5.42 meters per second. Awesome. Okay, now, okay, what do we want? We want F max. Okay, wait a second, hold on. Yeah, okay. All right. Okay, so let's just do it, right? Let's just do it. All right, so again, so J equals F average delta T, which is MV final minus MV initial. But this is where the impulse momentum goes. So final is 2, initial is 1. Okay, so we can do that, right? So that's M V2 minus V1. So the mass is 0.22 kilograms. Then V2 is 5.42 meters per second. Minus, a minus is plus, so it's plus 6.26 meters per second. So you get, that's the impulse. Oh, and I don't have it calculated, so sorry, you'll have to do that on your own. Okay, but that's all right. So therefore, F average is just the impulse over the delta T, which is this thing, 0.2 kilograms times that, 5.42 meters per second plus 6.26 meters per second. All right, divide by delta T. What's delta T? 5 milliseconds. So 5 times 10 minus 3 seconds. Okay, so that's F average, but what we really want is F max, which is twice that. So let's just say F max equals twice that, which is twice that, which is twice that. And that's what I have figured out. So you do that, and I promise you, you get 934 newtons. Okay, well, there you go. All right, so again, this was kind of a weird problem because, you know, they usually ask us for the maximum force, but the only way we could get it, because it says right here, the average is half the max. So impulse momentum allows you to get the average. So you just had to remember the entire impulse momentum theorem. And if you do that, you get the problem. So